Hey, good afternoon. Andy Sutton from BT. I'm a network architect responsible for our radio access network architecture and mobile backhaul, but also for our wider kind of satellite communications and fixed link architecture and strategy. So today I'm going to be talking about how we use satellite communications in the mobile network predominantly. But I'll start with a little bit of background about BT and space-based communications, look at some existing use cases for satellite and mobile backhaul. When we talk about mobile backhaul, we refer to the connectivity between a cellular radio base station, so the tower or column or rooftop radio site you see, and the core network. So traditionally, we deliver that connectivity with fiber optic cable or microwave radio, but in some cases we use satellite, and in other cases we deliver it with terrestrial, but use satellite to provide resilience, so a higher level of availability. We'll then introduce the concept of satellite orbits and kind of LEO mega-constellations. We see a lot about Starlink, and we heard from our friends from OneWeb yesterday. We're working very closely with OneWeb, so I'll talk a little about that as well. And then introduce the concept of 3GPP non-terrestrial networks. So you may have seen some announcements recently from SpaceX and T-Mobile USA talking about direct-to-device communication, so direct to commercial smartphones. We'll explore that as well, and then just a brief summary. Photograph in the background, though, the large antenna is our satellite communications centre at Madley. And on the right-hand side there, you can see a VSAT antenna on a cell site pointing at a geostationary satellite. So BT's got a rich history and extensive experience in the space sector. Here's another one of our installations. We traditionally worked a lot with geostationary satellites, so traditionally orbiting the equator, and we provide a wide range of services globally on geo. We do some work on medium Earth orbit satellites as well, but a lot of our focus now is on what we can do with these new low Earth orbit mega-constellations. We use a lot of portable-based satellite communications as well. They give a lot of flexibility in terms of being able to roll into a location and establish communications. You can see a couple of examples there on an emergency response vehicle and on one of our surveillance vehicles. Again, that flexibility, but both connected to geosatellites today. Geosatellites are great in as much as they're there. They deliver a lot of capability, but in terms of the bit rate and the latency, it's kind of constrained a little bit. So LEO should give us some benefits in that regard. Comes at a cost of slightly more advanced infrastructure to manage the system. So there's play-offs with both. We're not advocating one over the other. We're very much developing a kind of multi-orbital space strategy. So in terms of current use cases today for mobile backhaul, well, the obvious one is providing cellular radio coverage, 4G, 5G, in rural areas where we can't deliver a fibre or indeed terrestrial wireless, be that microwave or millimetre wave radio. But actually, that's not the most extensive use case we have on the network. The most extensive use case is for network availability uplift. And this is really quite important now. So we've got around about 750 terminals deployed for this particular use case across the mobile network, the EE mobile network. And the idea is if we lose terrestrial connectivity, certain services fail back to satellite. Now, clearly, there's less capacity on the satellite, but for the maintenance of critical services, then the capacity is adequate. Other use cases include rapid deployment. So quite often, if we want to build a cell site and connect it to the network, we could be waiting for wayleaves to deliver fibre optic connectivity, or indeed a radio channel assignment from Ofcom for a point-to-point microwave radio. We can deliver satellite capability, we can integrate the site, we can start to offer service, and then deliver the terrestrial transmission once it's available, and either leave the satellite if it's needed for resilience, or indeed remove it and redeploy. Other use cases, of course, include disaster recovery, tactical coverage, special events, and in the future, as I mentioned, and we'll touch on a little later, direct-to-device communications as well. So what does the high-level network architecture for mobile backhaul over geostationary satellite look like? So the user equipment, the mobile phone or MiFi device or IoT device, whatever it is, connects to the eNode B, so the 4G base station in this particular case over the radio interface. We then build an IPsec tunnel within that base station for security purposes, and traditionally we'd connect that all the way back to an IPsec gateway in the core. But actually, because of the latency involved and the fact we have to implement TCP acceleration for the geo satellite link, we have to segment the security domain. So we then terminate in that block that I've called VSAT there, and that hides a lot of things, as I've mentioned in the text at the bottom. We've got the actual satellite modem itself, in this case from Gillette. We've got TCP acceleration implemented on the MEC platform within that. We also terminate the IPsec, but then we map into an AES 256 security association across the satellite link. And we've also in there got the kind of Ka band radio transceiver and the actual antenna system itself as well. The satellite is just a bent pipe. So we just send a signal to it, turns it round, sends it back down to Earth. We don't do anything to that signal as such, which is quite different to some of the kind of more advanced concepts being explored now within 3GPP for deploying base station infrastructure actually on the satellites, particularly on LEO satellites. So, we've got kind of regenerative payloads. And again, we'll explore that in a little while. So we arrive back down at the Earth station. We then actually terminate the encryption that comes over the satellite link, re-encrypt in the IPsec tunnel. Same as the other ends, we use authentication headers and we're using encryption here. Over the terrestrial transmission, and that's completely diverse, to an IPsec gateway before we hand off into the EPC, the Evolved Packet Core. So that's the system we have in place today. As I say, that may be deployed in parallel with terrestrial transmission for resilience, or indeed it may be deployed on its own for particular other applications, particularly remote areas, or indeed the mobile vehicles that you saw before. So let's look at that resilience use case in a little bit more detail, because this is really quite critical. So if we look at a typical architecture, so topology for a cell site, we've got some fiber optic connectivity there between the core network and cell site number 1. We've then got 2 microwave radio hops, so we've kind of got a linear chain effectively going out from that fiber point of presence out to cell site number 2 and onto cell site number 3. Now, if we were to have a failure of that fiber optic connection, then, of course, we would lose all 3 sites unless we had some backup. Now, if we lose 3 sites, chances are we've got a coverage hole. Generally, on a cellular network, generally, not always, if you lose a single site, you've got overlapping coverage. So you've generally got some coverage, particularly outdoors. So what we're actually doing here is protecting against that loss of coverage by deploying a SATCOM capability to cell site number 2. So we lose the fiber, cell site number 1 then just routes its traffic the opposite direction over the microwave radio to cell site 2. Cell site 3 continues to work as normal. It just then maps its traffic onto the satellite link, and of course cell site 2 is co-located there. So we can maintain service, albeit with reduced capacity. The rapid response vehicles, again, make use of satellite communications. Example there with the GEO VSAT terminal. 800 megahertz, 1800 megahertz 4G on the vehicles. You can deploy those anywhere and have them up and working within 30 minutes of being on site. You could, and we are now developing a complete 5G private network solution that's going to sit in the vehicle and use a satellite link to provide an N6 interface, so connectivity out to the internet or indeed back to any private intranet or service platform as you wish. So new space is an interesting term. When we talk about new space now, we're often referring to all the activity that's happening in low Earth orbit, and indeed activity that's happening kind of on that boundary of space, maybe around the stratosphere as well, with high altitude balloons. So representation here from OneWeb. We've signed a global supplier agreement with OneWeb, so we're using OneWeb capability throughout the world. And you can see the different primary orbits here. This isn't exclusively all the orbital patterns you see. There are other elliptical patterns, but you can see the differences between GEO, MEO, and LEO here. So low Earth orbit is of great interest to us because we can reduce latency. The satellites are closer to Earth, so actually we can get smaller beam coverage patterns on Earth as well, which means we can increase capacity density, which is absolutely critical. And that's the reason why we're actually looking at HAPS as well, high altitude platforms, to get aerial objects that are closer again to Earth. So if you can really control that beam pattern on the planet, you can maximize capacity, minimize interference, but also enable the coexistence of spectrum on the terrestrial network and the space-based asset. And that's really valuable because spectrum is the very lifeblood of mobile networks. So let's explore those constellations in a little bit more detail. There are two primary constellations today in low Earth orbit that are operational. We've got Starlink and we've got OneWeb. There are two others in test and development phase, Telesat Lightspeed and Amazon Kuiper, both of which have plans to launch, again, your LEO-based constellations. Will we end up with 4 long-term? Will there be some mergers? I don't know what's going to play out there. Obviously, space is an expensive game to play in. But interestingly, LEO satellites are a fraction of the cost of a geostationary satellite. But of course, you need a lot more of them, so still a kind of expensive game. LEO satellites, as we saw on the previous slide, operate between 200 and 2,000 kilometres. Starlink are about 550 kilometres above Earth. So to put that into context, the space station, International Space Station, is about 475 kilometres, so they're sitting above that, and then OneWeb are further out at 1,200 kilometres. So OneWeb is planning on about 648 satellites in total, which includes some in-space spares. And there's various numbers being quoted in terms of what will happen in later phases of development and how densely packed these constellations could become. If you look at FCC rulings, for example, potentially as many as 6,000 in a future constellation. Each satellite provides about 7.2 gig of downlink capacity. Starlink have got thousands of satellites live now. And again, potentially scaling to 12,000 satellites in the fullness of time. So huge number of satellites in that low Earth orbit. So again, that densification gives us more and more capacity. And currently they're providing about 16 gig of capacity per satellite. Now, today, there are no inter-satellite links in operational use. So inter-satellite links being tested by the providers. But primarily, even with a LEO solution, you'll go up to the satellite, it's a bent pipe, and you'll come back down. So with LEOs, that means you need lots of ground stations or kind of ground gateways, effectively. OneWeb, the coverage in the UK is currently served from several European gateways, connected to a dedicated UK POP. And Starlink have got 3 ground gateways in the UK at the moment, again, connecting out to UK POPs for connectivity into service providers. You can see on the photograph there, this is the Madley Communications Centre, and you can see the dual parabolic user terminal that's been trialled. This is an Italian system, so working with OneWeb, that system is one of several that we now have live in our network for test and evaluation purposes. The 2 parabolic antennas are mechanically movable antennas. So you can see the size of them. You can understand the issues potentially with mechanical antenna systems. So we're working closely with OneWeb and with the wider industry on the development of flat panel phased array antennas, and you'll see an example of that in a moment. And here it is. We'll come on to that in a moment. So we've got 3 lab-based installations at the moment for testing purposes. We've fully integrated OneWeb into our network. We've built dual 10 gig interconnects into 2 21C POPs, so straight into our IP networks. We've got diverse routing into that network. We are connecting at several points around the world as well, so we're going to have globally diverse connectivity into OneWeb's constellation. This solution enables guaranteed end-to-end QoS, and this is where the business models really start to differ now between Starlink and OneWeb. Starlink are focused heavily on business to consumer, kind of best effort internet type access. OneWeb are really working with communication service providers globally to interconnect directly. So you're not actually using the internet as a backhaul technology between the satellite provider and the communication service provider. You're interconnecting directly, and you can implement quality of service on the satellite. So if you need QoS, you can actually do that within the satellite's capacity and through your interconnect, of course, to guarantee that end-to-end performance. So that's fundamentally quite different. So we've got an operational base station today in a rural area that's got satellite-only backhaul, today via a geostationary satellite, working with our colleagues from Avanti on the HILAS 4 satellite. We've also got in parallel with that a live deployed OneWeb terminal, and later this month we will switch from one to the other and start to do some further evaluation. As I say, it's not necessarily a case of LEO will replace GEO. There'll be use cases where we want one or indeed the other, or actually where we want to deploy multiple orbit capability for resilience. We've also got several friendly UK and global enterprise customers who are now doing live activations with us for trials. I mentioned the requirement for flat panel antennas, far more deployable, and you can see an example here from Kymeta. We're also expecting terminals from Telion and Hughes as well in the fullness of time, and we're going to be evaluating these and looking at the various deployment scenarios and indeed opportunities they open up for us. So we've talked a little bit now about mobile backhaul. I want to use this slide to kind of make that transition a little from mobile backhaul to direct-to-device communications as well. This slide is an internal diagram that starts to show some of the kind of wider applications and implementations of non-terrestrial networks. I'm not showing GEO on the slide purely because I was kind of vertically challenged to fit everything onto the slide here, but assume GEO's there as well. I have shown an intersatellite link, which is really quite a key enabler for networking with LEO satellites, because that really does open up coverage across the entire globe. Even if you can't position a suitable ground gateway, you can connect via an intersatellite link to another node. I've mentioned HAPS on there as well, high altitude platform systems. We're doing a lot of work at the moment with a company called SPL, Stratospheric Platforms Limited, and we're looking at how we can use HAPS platforms to again further enhance the capability we have in that wider NTN space. We think about drones in a broader context though. We're going to have lots of drones in the sky. We're going to need some order. We're going to need to do some geofencing. We can use technologies like 5G to provide that geofencing. We can use these kind of technologies to control the drones, to backhaul to and from the drone, but also, of course, we can put network infrastructure on drones and have drones deployable for certain scenarios, including disaster recovery. So drones are really important as well. And then the other aspect of the diagram is air-to-ground. There are now 2 air-to-ground networks in the UK. One is a European aviation network, which is run by Deutsche Telekom across the whole of Europe. And the network aims to deliver connectivity to commercial airlines. It uses spectrum from the ground and the same spectrum from satellites and the discrimination of the aircraft and the antennas to be able to increase the capacity and reduce latency when you're over airspace. Of course, when you go out of the ocean, you're going to drop back to just a satellite. And then also, of course, we've got the emergency services network, which provides air-to-ground services for helicopters as well. We do foresee the need for a commercial air-to-ground network as we start to get more drones in the sky. So some interesting opportunities there. So enhanced mobile backhaul, or enhancing mobile backhaul, we've talked a little bit about these scenarios already along that top line. So if we can get fibre, of course we'll put fibre in. If we can get terrestrial microwave, we'll put that in. If not, we'll use satellite. And where we need to, we'll use satellite to augment the availability as well. The bottom, direct to handset. So 3GPP, Third Generation Partnership Project, is a global body that's standardised in mobile telecommunications, and they're now working on direct-to-device. And the important thing is here, this isn't a specialist satellite phone, it's direct communication to your off-the-shelf iPhone or your Android phone or whatever is your particular preference. Now that's really interesting and brings in some really interesting challenges from a link budget perspective, particularly for the uplink from the device to the network. So don't expect gigabits per second of capacity from these systems, but actually in terms of having access to messaging and then maybe some basic voice services, some basic IoT, there's some really exciting opportunities here. But again, HAPS is a big part of that story as well, as we say there in the last little box. So what are the roles for non-terrestrial systems in 5G, and why has it really caught the imagination of 3GPP? Well, really building on the ecosystem, because the reality is, of course, we've got this global standard now that is 5G. The first time we've had one single standard with one of our generations of mobile. There are even two in 4G, albeit LTE clearly won that particular battle. But we've got one standard now. So we've got a huge mass market economy of scale. And that fundamentally changes the economics of building networks, and including building satellite systems as well, particularly when a lot of the software that we need can be commoditized and uploaded to the satellites as required. Interesting thing with high altitude platforms, of course, is periodically they're going to come into land. So you can do maintenance on them. You can swap the antennas. You can swap the batteries. You can change hardware if you need to as well. So again, different concepts here in terms of how we use different platforms. So basically the diagrams here show the different scenarios 3GPP is exploring. From the mobile backhaul scenario we discussed at the top, the bent pipe, satellite and back to Earth, to the use of inter-satellite links in the middle there, where we're actually communicating with one satellite and then transiting through one or indeed more satellites to get to the ground station. And that could be useful, for example, if we're in the middle of an ocean. And then the direct-to-device communication you see at the bottom. Now, that direct-to-device communication opens up some really interesting scenarios and some interesting kind of research questions around the base station itself. And I mentioned the need or the ambition to have regenerative payloads on low Earth orbit satellites. So, do we actually put the base station on a satellite? That's a really interesting question. Or do we put a subset of the base station? Through initiatives in 3GPP, and indeed through the Open RAN Alliance, we now see the radio base stations can be decomposed into a number of functional components with standardized interfaces between them. So we have options to look now at how we place more active electronics and more optimization into the satellites. Bearing in mind, of course, that a LEO satellite, very different to a GEO satellite, is expected to have a lifespan of maybe 5 to 7 years. So that's a typical kind of return on investment that you would expect from a base station investment, as opposed to maybe the 15 years, and indeed longer now as we start to get the ability to refuel the larger, more expensive GEO satellites within their orbital pattern. So this slide just looks at different ways of decomposing that base station and providing different interfaces back to Earth. So the conclusions from that 3GPP study were actually that, yes, we want to do this, because what's it going to give us? It's going to give us ubiquity, mobility, the ability to do broadcast, and indeed the ability to build resilience. So primarily, if you can access a terrestrial network, always do it. It's going to be cheaper. It's going to be lower latency. It's going to be far better performance. But actually, if that's not available, and you've got a mission-critical application, then actually drop into a non-terrestrial network will be advantageous. There will also be areas where it's not commercially viable to deliver terrestrial infrastructure. So again, satellite communications could fill that particular area as collectively as an industry we deliver 100% coverage of the globe. We're actively engaged in a range of projects within the ecosystem. Here's an example of one, the SAT5G project. All the deliverables from this project are available to download on the internet, all freely available. It was an EU-funded project. You can see, a real wide range of collaborators on the project here. We worked closely with the University of Surrey on this particular project and the Surrey satellites. And a whole bunch of partners bringing modems, bringing antenna technology, bringing space-based assets as well to the project. So, a lot of the output from this fed into 3GPP and triggered that work on non-terrestrial networks. So to summarise, prior to taking some questions, a real whistle-stop tour through the integration of terrestrial and space-based communications. I did originally submit the 4-hour version of this presentation, but was told to keep it short and snappy. Okay, so let me summarise. Non-terrestrial networks, it's receiving a massive amount of attention at the moment. And that comes with a massive amount of investment. So there's huge amounts of money going into this and lots of opportunity. The integration of terrestrial and space-based communications enables truly heterogeneous networks. And that brings with it greater resilience and reliability. So the services you need can be delivered over multiple networks. We have technology such as SD-WAN that allows us to integrate a wide range of different technologies and build different levels of availability and use case performance. So we need to embrace them and bring all these technologies together. A multi-orbital space strategy provides complementary connectivity to support an integrated terrestrial and space-based strategy. This is really quite important for us. There are some advantages to GEO, there are some advantages to LEO, there are some advantages to HAPS. It's a case of understanding how we use that entire portfolio to deliver the optimal service for our customers. So LEO is a really exciting new addition to this. We're massively excited by LEO, lower latency, higher system capacity, higher data rates, and 3GPP direct-to-device comms is a useful complement to terrestrial infrastructure, but it most certainly isn't a replacement. So thank you very much. Just about on time, I think. Thank you.
Thank you very much, Andy. Any questions?
So
Hello.
Two questions.
Yeah, please.
So the inter-satellite communications, you mentioned it, but says nobody's doing it yet. Mm-hmm. Do you have any feedback or any perspective into when that might be a realistically available service? Because the actual physics of moving objects whose orbits decay, connecting to each other, is rather challenging.
It is indeed, absolutely. It is live now within the Starlink network from a test perspective. So they do have some Generation 2 satellites launched. There are a couple of primary options that are becoming popular in this regard now. One is E-band radio, but actually the most popular application is optical communication. So laser-based communication effectively. So being trialled now. When will it be available across multiple constellations mainstream? Well, I would expect Telesat Lightspeed and Amazon Kuiper to launch with it from day one. It'll be there by that point. So I think we're talking maybe 3 to 5 years we'll start to see this becoming more mainstream. Yep.
And the other question is, a lot of what you said, at least I read it as essentially replacement for fixed backhaul. But what would be really interesting is what's the capability going to be for turning up and turning down big increases in bandwidth in a particular spot position for events and disasters and other things where all of a sudden the world changed and you need a whole bunch of capacity you couldn't have before. Absolutely.
And the answer to that is always to put a fibre in or terrestrial microwave if you can, but where you can't, this is why we favour a multi-orbital and indeed multi-constellation strategy. So effectively being able to connect through a router to multiple providers, let's say OneWeb and Starlink, for example, plus also have a geo connection. Then it gives you a lot of flexibility. You can make decisions then as to what traffic types you need to route where, but it's definitely all about multi-constellation, multi-orbit to maximise flexibility. And as soon as we start to get modems and terminals that allow us to do that in an integrated and cost-effective way, that becomes quite game-changing. Couple that, of course, with direct-to-device communication as well. And then you've got quite a flexible toolkit all coming from space. Thank you.
Hi, Andy.
Hello,
Thank
Tom.
you very much for this. I was curious. I was at a satellite networking side meeting at the IETF last week, and they made the assertion that not only would some of the base station pieces be implemented on satellites.
I believe they will,
they suggested that we should have edge computing functions in these satellites as well. Do you see that as realistic? And I don't think it was mentioned in the presentation.
It wasn't, only in the interest of time, to be honest with you. Part of the broadcast narrative that came out of 3GPP was exactly about that. So if we're increasingly flying satellites with x86-based compute on board, for example, and we can run a software-based user plane function on there that can sit behind the back of that base station and interface into some kind of service platform, then we could distribute content and use them for broadcast as well. And that could be a host, a reason for having the MEC and having that content hosted up there. The MEC platform, depending on how you define MEC, could indeed be the compute platform that hosts some of these services. There's really two definitions around MEC in terms of what it means in ETSI and what it means in 3GPP, really.
And I also had a little interest in the HAPS sort of solution. Of course, Google had their Project Loon.
They did, yeah.
But they shut it down.
Yeah.
And I thought there was perhaps something that they figured out that I don't know if we've learnt from in this case. I mean, I recall thinking there was a lot of effort that went in to start trying to predict and account for weather patterns and various other things. But do we know how we've solved that problem? Are we hoping?
I think that's more of a business thing. I think we're more realistic now in our expectation. I think we talk a lot now about the integration of terrestrial and space-based assets to deliver that capability. There was a lot of talk early on about we're going to use satellite and we won't need terrestrial. We're going to use HAPS and we won't need terrestrial. That is absolutely not the case. These are complementary technologies. They're very different cost points, very different performance requirements against each one of them. So they need to be used together to build that heterogeneous network. And I think it's that maturity of thought as an ecosystem that's now come together in 3GPP.
Okay, thank you very much.
Thank you.
So I'd just like to say, Tom, before I ask my questions, I just don't want to keep you hanging around. You have been the single most engaged member of the audience. You have the most times come up and asked thoughtful, pertinent questions. So you win the prize for that, which is a custard tart from the Chinese bakery up the road.
Hey. Well, Tom.
I've got one question of my own,
Please.
and then a few from remote.
Perfect.
The high-altitude platforms you were talking about, it might have just been an artifact of the graphic, but that almost showed them being above aeroplanes. What is high altitude in that context?
And that varies considerably. Some of them are actually at a similar altitude to aircraft. So obviously there's an air traffic control aspect to that, and those conversations are happening as well. But certainly no higher than the stratosphere, and often quite a lot lower. The lower you can bring them down, the more concentrated you can make the beams, the more localized you can make the service area. So again, there are applications for that as well. So it will be everything in between, to be honest with you. Yeah.
Sure. So we have questions from Kathy, who has asked, on behalf of astronomers wishing for a darker and less obscured sky, is there any work going into making satellites less visible?
Absolutely. In fact, Starlink kicked off a lot of work very early on because of issues with some of the early satellites that went up. The LEO satellites, as they typically have a lifespan of 5 to 7 years, and then generally they kind of dropped and burn up on re-entry. So there may be some satellites up there that will be replaced at some point in the not too distant future as well, which will now go up with a new configuration aimed at addressing exactly that issue. It's really important. I like astronomy myself. Yeah.
Another one we've had is, what are the practical vulnerabilities of the satellite end of the satellite communication networks? Are they liable to be targeted by those who wish to destroy communication networks for whatever reason, or is this just not practical or cost effective? How many could you take out in a single shot?
And that's a really interesting question. It's very likely that the missile system required to target and destroy a low Earth orbit satellite would cost more than the satellite. So, is it financially viable? Clearly, there are effects that could be caused that could impact multiple satellites in that regard, particularly the amount of space debris that would be caused as a result of that. But these things, typically a LEO satellite is about 250K. So, relatively low cost in the terms of space. And they're about the size of a washing machine. And they're travelling at feral speed as well, so they're not going to be easy things to target, hit and destroy. But it will be possible, but it'll be costly. Yeah,
definitely nation-state levels of
completely, absolutely, yes, without a doubt. Yeah.
Last call. Any other questions?
Great. Well, thank you for the engagement.
Thank you very much.
Cheers. Thank you.